I want to go through this, check your understanding. So if you were stuck on any of these pieces, I kind of want to talk through this to make sure that we understand it, and then we're going to start on the next set of activities/notes. So check your understanding. I realize my text is very small up here, but you've got the same thing on your page in front of you. So if there is a uniform distribution, it tells me that it's uniformly distributed over the interval from 40 to 50 inches. So everybody is choosing between these. So if I'm thinking about my y-axis, since we have 10 inches here, this height right here is 1/10 because the area has to add up to 1. So what height must the density curve have? Area is equal to 1. And we have 10 inches. And so the height would have to be 1/10. Remember, on a density curve, it's always going to add to 1. The area is always going to be a sum all the way up to 1, because that's the same as 100% of all of the observations. Area is equal to my proportion. So that 1 is really saying 100%. Anytime in statistics we see the whole number 1, it is the same thing as 100%. Yes, ma'am? The 10 because from 40 to 50 inches, if I take where they stopped, so biggest minus smallest, I'm basically finding the range. That's how I'm getting that 10 inches right there. Does that make sense? So it's spread out evenly. That's what that uniform distribution means. It is evenly spread out over those 10 inches. So every 1 inch mark, we've got 10% of this population that chose a value in that range. Does that make sense? Over the 10 inches, 10%, now I'm at 100%. All right. The percentage of guests that cut their yarn longer than 48 inches. 48 inches would be about where on my picture? On the picture of my distribution. In between 45 and 50. Probably closer over there to the 50, right? So if 48 was right here, I want to know what proportion of people fit in that shaded space right there. How many inches are we looking at? 2 inches. So from 48 inches to 50 inches, because nobody went over 50 inches, this is 2 inches. And the height of each of those bars is 1/10. So I would take 1/10 times 2. Can somebody grab their calculator? 1 divided by 10 times 2 would be what? Give it to me in decimal form if you can. 0.2. So what percent of people? 20% of the guests cut yarn longer than 48 inches or longer. Calculate and interpret the 25th percentile of this distribution. So the 25th percentile means the area under my density curve would be equal to 0.25. So I'm going to approach this very similar to what I did up above. .25 spread out over 10 inches. So I'm multiplying it by 10. What would I get? What'd you say? 2.5. This number right here would go from my minimum and then up 2.5 inches from there. What was the minimum amount that somebody cut their yarn? 40 inches. So I'm going to do 40 inches plus that 2.5. I get 42.5 inches. So 25%, that's what my 25th percentile tells me, 25% of the guests cut their yarn at 42.5 inches or smaller. All right. So those are all the parts of question 1. Question 2 is talking about normal curves. Our normal curves, this is our bell-shaped curve. We labeled it right at the end of class yesterday. So they want us to draw in a normal curve here. And we need to label this. Right in the center is where my mean goes. I'm actually going to draw this off to the side so that I have some more room. There we go. I don't want to do it too small. So this is what a normal curve looks like. The mean goes right in the middle. And we use this Greek letter mu to symbolize the mean. So what I would put right here in the center, and I'm going to have mean equals 44 inches. And then we want to label 1, 2, and 3 standard deviations on either side. So 1, 2, 3. 1, 2, 3. And I need to label those as well. What did it tell us the standard deviation was? 4 inches. So as I move to the right, I would be adding 4 inches to my mean. And as I move to the left, I would be subtracting 4 inches each time. So let's move to the right first. We started off at 44 inches. 4 inches bigger, one standard deviation would be what? 48 inches. For my second standard deviation, I'm going to add 4 more. What would that be? 52. And then for my third standard deviation, I'm going to add 4 more. 56. So I have 3 standard deviations to the right. My mean is 44, and then it's 48, 52, 56. Going to the left, I'm not adding anymore. Now I'm going to be subtracting 4 each time. So what would my first standard deviation to the left be over here? 40 inches. And then what? 36 and 32. anytime we are drawing a normal curve, we're going to have to label it like this. We're going to have to put the mean in the center, and we need to do 3 standard deviations on either side. The other thing that we have to do when we have a normal distribution is we have to label this. I need n to tell me that it is a normal distribution, and then inside parentheses, we're going to have our mean. What was our mean here? 44. And then I need my standard deviation, which we use a sigma to represent. What was our standard deviation? 4. So we always have to label our normal curves. A lot of times we won't include the units right here, and we won't necessarily put mu in there equals 44. We have to have them labeled with the values. But then this over here tells me what my standard deviation is, what my mean is. All right, who remembers from yesterday, from right here to right here, 1 standard deviation on either side. This is what percent of my population? 68%. What about 2 standard deviations on either side?
97.
Close. 95%. 2 standard deviations. And if I go 3 standard deviations on either side, that is 99.7%. They want to know about what percent of women who are 8 months pregnant, which is what this normal curve is showing me, have a waist circumference that is less than 40 inches. Where's 40 inches up here? 1 standard deviation. So that, less than 50%, right?
Yeah.
50% would be right there in the middle where the mean is. If I could figure out how much this was, I could do 50% minus that piece to get the area that's below it. If 1 standard deviation on either side is 68%, what is just 1 standard deviation? 34%. This space right here is 34%. So I would do 50% minus 34%. And what do we get? 16%. So 16%. Oh, sorry, that should have been the next question down. I wrote it in the wrong part. 16% would be the percentage of women who are 8 months pregnant with a waist circumference less than 40 inches. A waist circumference greater than 52 inches may indicate excess amniotic fluid. What percent of women who are 8 months pregnant may have an excess of amniotic fluid? What can I use to figure this out?
99.7.
Where's 52 inches? Yes. 52 inches, that is the second standard deviation. I know if I go 2 standard deviations on either side, that catches how much of my population? 95%, right? So if I look at these 2 little tails off to the side, I'm looking at this tail here and this tail over here. Those 2 together would be 5%, correct? I have 100% of my population minus 95%. That's 2 standard deviations on either side. But I'm only interested in just the one tail, just the ones bigger than 52 inches. Right now, this 5% is on either side, equally balanced. How do I find just one of them then?
2.5.
Yep, divide the whole thing by 2, so 2.5%, yes. 5% is both tails. We're going to take that and cut it in half so that we get just the one tail. So 2.5%. Those would be the women at risk. I'd heard that there was a question on the very last homework problem, the one on the back side, number 5. It gave you an equation for miles traveled and fare paid. And it told you that this particular customer calculated the mean and the standard deviation of his fare, right? The amount that he had paid. And it asked you to find the mean and standard deviation for the miles. You can use that equation. Take the mean of his fares paid, substitute that in for fares in that equation, and then work backwards. So you're going to isolate then the miles traveled. And then you would do the same thing for the standard deviation. You're going to substitute into the same equation with 2 different values. One would be the mean fare, and so then from that you can find the mean mileage. The other one is the standard deviation of the fares. So when you substitute that in, you can use it to find the standard deviation of the miles. Does that make sense? Absolutely. So what does it tell you the mean amount of money he paid was?
$15.45.
$15.45. Okay. So the mean fare, $15.45. And what was the equation that you had to work with?
$2.50 plus 2 times the miles.
You said $2.50 plus 2 times the miles equals what?
Equals fare.
Equals the fare. So I would take this $15.45, I'm going to put it in the place of the fare right here. So I would have $2.50 plus 2 times the miles is equal to $15.45. And then from here I'm going to solve it like a 2-step, Algebra 1, Algebra 2 style. What would I need to eliminate first as I'm trying to isolate miles? 250, so I'm going to subtract 250 from both sides. So I'd have 2 times the miles is equal to 13, what is that, 1195? Somebody check my math, I don't have a calculator in front of me.
It's $12.95.
1295, thank you. 1295. I thought I might have subtracted 1 too many. And then to find the number of miles, I would divide by 2. And then I would do the exact same thing for the standard deviation. So this is going to tell me the mean number of miles, or the average number of miles. Does that help? Okay. All right. We are going to be on the page that has Back to the Future and a picture of the DeLorean and a very, very young Michael J. Fox. Right here. We have what information about the DeLorean that we are supposed to use to label this thing with? What information do we have? Yep. We have the mean, and we have our standard deviation. We're going to use this. We're going to label the curve. We're going to break down these percents since this curve is drawn much, much bigger so that we can figure out what all these pieces are so that we can go down and answer the other questions. We will not get all the way through this today. We'll finish this up tomorrow, and then we'll continue building on these ideas. Okay? So on my normal curve, what goes right in the middle? Mean, which is 80. So here's my mean of 80. One standard deviation over, how do I find that?
7.213.
What was our standard deviation again?
7.7.
7.7. So I'm going to add the mean. That's okay. And I'm going to add 1 standard deviation to that. So I would have 87.7 here. 2 standard deviations over, I'm going to take my mean and I'm adding 2 standard deviations. So I have to add 7.7 twice to the 80. 94 or 95.4. And then 3rd standard deviation, which is way over here. This is my mean plus 3 times my standard deviation. 103.1. All right. I think adding is the easier way to go. Let's go to the left-hand side now, and we're going to do some subtraction here. So off to the left, I have to take my mean, and I'm going to subtract 1 standard deviation. 72.3. 2 standard deviations. I'm taking my mean and subtracting the standard deviation twice. 64.6. And then for the 3rd standard deviation, which is way over here, mean minus 3 standard deviations. 56.9. We have to label our normal curves, always and forever. If it has this bell shape, especially if we are told that it is normal, you have to label it. So we label it with an N so that we know this is a normal distribution. And then what 2 pieces of information do I need? Mean and standard deviation. You do not have to label those as being the mean and the standard deviation, but you do have to have those 2 values in there. Like you don't have to say mu equals and sigma equals, but I need those 2 pieces. It is understood that in this set of parentheses, the first value you're giving me is the mean, and the second one is the standard deviation. That is consistent across all of statistics. So far, so good? All right. We know that this whole space in here is what percent of my total distribution? 68%. So how much is in each section? 34% in each of these. All right, we're going to do a little bit of math now. Yay. 2 standard deviations is how much of my total distribution? 95%. So if I have 95%, I'm trying to figure out what percent is in these 2 spaces here. I already know the center part, right? So I can subtract that out as I'm trying to figure it out. How much did we say that center part is that's not shaded, but I wrote on it in orange? 68%. $95 minus 68 would give me, is that 27? 27%. And then it is split evenly between those 2 sections. So what do I need to do to the 27% to figure out what goes in each of those? Divide it by 2. So I get, what, 13.5? You guys okay with how we've come up with these so far? Please tell me if I've lost anybody. If I go out 3 standard deviations, how much area is that? What is my percentage? Yeah, 99.7%. I'm trying to figure out what is the amount between 2 and 3 standard deviations on either side. I'm trying to figure out what values to put in here. 99.7 goes from one end and includes all this. But these spaces in here, this makes up what percentage? 95. So I'm going to subtract that out. Minus 95%. That gives me what? 99.7.
I mean
4.7?
Yeah.
4.7%, and then it is divided evenly between those two sections. So I need to take that and cut it in half to figure out what goes in each tail. 2.35. Please tell me if I'm losing anybody. All right. Last thing I want to know, these itty bitty tails, less than 3 standard deviations to the left. Sorry, I'm backwards from you guys. So what's smaller than 3 standard deviations to the left or bigger than 3 standard deviations to the right? What percentage would go in there? Well, this middle section that I've got is how much again? 99.7. So 100% of the whole thing, that's every piece as far as I could go in either direction, minus 99.7. That's going to leave me with how much? 0.3. 0.3%, and I have to split that between 2 tails. 0.15. So right here is 0.15%, and over here is 0.15%. I wanted to break that all down because when they're asking me to find these different percentages, I can use my empirical rule. It's really helpful, but only if I kind of know how it breaks down. From here to here was 68% total. From here over to here was 95% total. And 99.7 is almost the whole thing. I don't know if I have enough room to put that in there without it being confusing. 3 standard deviations on either side. So this part right here. It's 99.7%. Okay. What percentage of the runs will give the DeLorean a speed greater than 87.7 miles per hour? Where is that on my picture? 2 standard deviations. So I'm wanting to know, since it's greater than, I want to know what is this area right here. 16%. There's a couple different ways you could get there. Now that we have everything kind of labeled out, I could add up those sections. So I can take 13.5% plus 2.35% plus 0.15%, and we get 16%. You could do it by subtraction as well. That would be perfectly fine. You can do it as a combination of addition and subtraction. I want you guys to learn how to apply this empirical rule to answer questions, and there's more than one way to go about arriving at that correct final answer. We're looking at this area, and I want to know what's the area of that space. What about for number 3? What percentage of the runs will give the DeLorean a speed between 64.6 and 87.7? Where am I looking?
81.5%.
Tell me how you got there.
I just added them all up and then added 13.5.
Yep. So one standard deviation on either side, that's 68%. That takes me up to that 87.7. Here's including 64.6. So I've shaded it between 64.6 and 87.7. So I'm going to add 13.5 to 68%. Got 81.5%. So far, so good? Okay. What percentage of the runs will give the DeLorean a speed of less than 64.6 miles per hour? 2.5, yes. I would take that 2.35. I'm going to add it to the 0.15. You get 2.5%. Or you could say, well, we're going out 2 standard deviations on either side. That's 95%. But I only want the smaller tail, so that has to be half of 5%. Either way you go about it. What about number 5? What percentage of runs will give the DeLorean a speed less than 68.45? Hmm? 9.25. Tell me how you got it. I love it.
So I was looking at the number and I realized it looks kind of halfway between 64.6 and 72.3.
Mm-hmm.
So I divided the standard deviation by 2 and I got 3.85, and so I added that to 64.6 to double check, and I got 68.45. So then I divided the 13.5 in half, and I got 6.75. And so I took 6.75 and then added it to the 2.35 and the 0.15.
Yes. Yes. So we have 9.25 for that particular piece. However, when I'm looking at this, if I take just this piece, would that be half of 13.5? Area-wise. Is this section the same size as this section? No. I love your thinking. That's exactly the way I would have approached it. We're going to have to introduce a new tool to use when we're falling in between these standard deviations where we know our values. Do you guys remember when we talked about z-scores the other day? We're going to use a z-score here. So z is equal to my value minus the mean divided by the standard deviation. The value that they gave us to work with was this 68.45. What was the mean here? 80. And our standard deviation? 7.7. Go ahead and give me that value, and we will stop there for today then, and I'll show you how to interpret that value tomorrow. Negative 1.5. So we are 1.5 standard deviations below the mean. And we will use this value to find the percentage tomorrow. Okay? Homework 2.2. Due on, as of right now, due on Thursday. We'll see how far we get tomorrow. If we don't get through everything, I'll bump that out to Friday. Okay? But as of right now, homework 2.2 is due on Thursday.